Welcome everyone to this Monash Cybersecurity Seminar. Today we are very happy to welcome Dung from University of Wollongong. Dr. Duong got his PhD degree in mathematics from Leiden University, and after that he spent 2 years as a postdoc fellow at Faculty of Mathematics in Bielefeld University, and then 3 years as an assistant professor at the Institute of Mathematics for Industry in Kyushu University. And then he joined University of Wollongong in 2018 as a lecturer. And his current research interest is in post-quantum cryptography, which is also the topic for his talk today. And in particular, he will talk to us about post-quantum signatures from isomorphism problems of trilinear forms. Thank you very much, Dung. And the scene is yours.
Okay, thank you, Mohammed. So thanks. First of all, thank you very much for your invitation and also the host for my talk. So let me just start it. So today I talk about the post-quantum signatures from isomorphism problem of trilinear form. Okay, so the topic is about post-quantum crypto, and as you know that NIST they calling for post-quantum crypto proposal for standardizations, and the call for proposal in February 2016, and the deadline was like 1 year after that in 2017. So in round one, the deadline was December 2017. They announced like 69 eligible submissions, and 2 years later, well, not less than 2 years, they announced the round two, and there was 26 algorithms. In July 2020, they announced in round three there was 7 finalists and 8 alternatives. And it's just last month they announced the candidate to be standardized. So if we look at the candidate that they announced for standardizations, then in public key occams we have Kyber, and in signature we have 3 candidates with Lithium, Falcon, and Sphinx. And they also calling for a proposal on digital signature not based on structural lattice. We hope to see the some other submission in the future, not in lattice, because if you look at the candidate for standardization, then most of them are lattices, right? So that is something maybe NIST want to see some other candidate. Okay, so this is also the topic that I'm talking today. So today I will talk about new post-quantum digital signatures that is based on different assumptions. The assumption is on isomorphism problem of trilinear form. And if you look at the talk, if you watch the talk at the end, and you see that this will be in line with the direction of recent. If you look at the recent works on cryptography from group actions. Well, I mentioned that this is somehow potential for practical use. The public key size is roughly 4,100 bytes. Signature size around 6,800 bytes, and the running time also 0.8 milliseconds on common let-off. And this is based on the joint work with Gang, Antoine Cho, Thomas Plantach, Yuming Chao, and Willie Susilo in Eurocrypt this year. And if you want to look at the full papers, the full version is available in ePrint. Okay, so what is the idea of the construction? So the idea is very basic. The idea is we construct the zero knowledge interactive proof for alternating trilinear form equivalent problems. So this is actually inspired from the Goldreich, Mikali, and Wiedershen zero knowledge protocol for product isomorphisms. And then getting the signatures easy, just apply Fiat information. So basically, if you look at it, then what we do is we get the same idea of what GMW protocol for product isomorphism, and we replace product isomorphism by alternating trilinear form equivalent problem. So before going in the detail, then I would like to recall about the graph isomorphism problem and the protocols. So two graphs with the same number of vertices, they call isomorphic. If, after relabeling them, then they are basically the same. So formally, you may have a bijective map between the vertices in such a way that if the edge is in E1, if and only if the image of H is also the image of U and V, then so form an H in E2. And in this case, we write G2 equal to phi of G1. So the graph isomorphism problem saying that I give you two graphs and ask you to answer whether this is isomorphic or not. And here is the GMW protocol. So here the prover know an isomorphism that mapping G0 into G1 and try to convince the verifier that, okay, he knows that transformation. So what he does is, in the first step, he choose a random symmetric permutations. On N here, the graph contains of N vertices. So N is the number of vertices in the graph, and just the permutations and apply into the graph G1 to obtain the graph H and then send it to the verifier. So the verifier just send a challenge, just a random bit 0 or 1, and the prover just prepare the answer, the response. So psi equal to C times pi and plus 1 minus C pi composed with phi. And then send the response to the verifier, and the verifier to check whether this is correct. So if you look at this, and if C equal to 0, then this is pi composed with phi, and then if C equal to 1, then this is a pi, and it's easy to check that this is actually give you the correctness of the protocols. And the security of the protocols based on the hardness of graph isomorphism. And in the 80s, the best worst case algorithm for graph isomorphism, they run in time exponential of square root of n. However, recently, Babai showed a breakthrough in solving graph isomorphism in quad-C polynomial time. However, so that means this scheme were broken. However, the idea there were inspired a lot of designs, including the design in multivariate crypto, starting from the work of Patarin, when he replaced the graph isomorphism by polynomial isomorphism. And this includes several constructions, like hidden field equations or rainbow. In 2006, then Kovench, I hope I pronounced correctly, he proposed to use class group actions on elliptic curve to replace the graph isomorphism in GFW protocol, and this is somehow the born of, we know nowadays, the isogeneous based cryptography. So in our work, we replace the graph isomorphism by alternating trilinear form equivalence, what we denoted by ATFE. So what's the ATFE? So before going to ATFE, I would like to introduce about the group actions, because as mentioned earlier, this is in line with the area of group action, and everything is agreed price in terms of group actions. So let G be a group and X is a set. Then the group actions of G on X is just a map. Satisfy that if the identity element, the X on X, and it's just keep X the same. And you have associate what we call the compatibility, or we call the associativity properties, in the sense that if you act H on X and then you X with G, then it's similar to acting on X by GH. Okay. So the orbit of element in the set is defined by the set of all the resulting action of G on that element. The stabilizer of element is just all the element of the group that's fixing the element. And this is the subgroup of G. And if G is finite, then we have that the cardinality of G is just the cardinality of the orbit times the cardinality of the stabilizer. And the group action is transitive if the orbit cover the whole, sorry, this should be the whole X, right? So that's mean, what does it mean? This is not G, this is X. That means that whenever you have two elements in X, you always find an element G that maps this element to another element. So this is called transitivity. And this you may have seen in Diffie-Hellman, I mean in discrete log setting, and also in the isogenous crypto setting. Okay, so what's the alternating trilinear form? So now I denoted FQ, which is the finite field of order Q, and the trilinear form is just a map. And is it alternating if it's, I mean, a trilinear form is alternating if it's evaluated to 0 whenever you have two arguments that are the same. That means if you have two arguments at UU, or the first and the third, or the second and the third are the same, they are 0. Okay. And let GL and Q be the proof of n times n invertible matrices over FQ, then these have actions. So on ATF, so ATF is just a set of all alternating trilinear form over FQ to the power n that we define here. So how is about the action? The action is written on the right-hand side instead of the left-hand side, okay? So the action is described by the following. So if you have the action of on alternating trilinear form will be resulting in one alternating trilinear form such that if map UOW into this one. Yeah. And this will define an equivalent relations on the set ATF, that is on the equivalent relation on alternating trilinear form. We denote it by this. So this is phi and psi are equivalent if and only if they are just the resulting of the other under the actions of one element in the general linear group. And here are some assumptions or some problem that for the alternating trilinear form equivalent that you may have, you may suspect. The first one is decisional, similar to the one we see in graph isomorphism. Given two alternating trilinear form, decide whether they are equivalent in the sense that whether there exists an element in GLNQ such that it's map psi to phi. And then we also have a promise version in the sense that, okay, I give you two alternating trilinear form with a promise that they are equivalent. Can you find an element that maps this element to another element or not? For the cryptographic purposes, I mean, for the design purposes, we have the M alternating trilinear form saying that I have M alternating trilinear form so that they are equivalent. So can you find a pair of elements in such a way that you can find an element A that maps this phi I to phi j or not? So the thing is not known whether the promise can reduce to decisional ATFL or not. It's expected in time Q O to the power n, but we don't know kind of polynomial time reduction. And if you look at this, and it's maybe easy to get a non-time reduction from the M from promise problem into the promise problem. But here we assume that the M instant promise problem is hard. It's hard at the one instant problem. Okay, so before going to design describe the schemes, then let's look at the hardness of ATFE. So we will consider several aspects of the hardness. We will look at the average case hardness of ATFL. We look at the worst case hardness of ATFL, and we also look at the algorithms for attacking ATFL at the moment. From that, we can provide some complexity estimation for ATFL, and then this is the tool for us to extract the parameters for the schemes. Okay, so the first one, if we look at the worst case hardness of ATFL, so this go back to the work of one of the college in the paper with his college, Jo Yumin Chao. So Guo Chou and Chao, they introduced what they call the tensor isomorphism complete class. And then with Dung, they proved that ATFL ETI complete. Okay, and let I introduce a little bit about what does it mean by TI problems that have to support the worst case hardness of ATFL. So a D tensor is just a D-way array. Okay, so if you look at 3 tensor, for example, then this is just a cube of numbers. Yeah, we have this cube of number, and every face here is just a matrix. So if you look at 2 tensors, and this is just a matrix. Okay. And then what is because there exists a reduction from D tensor to 3 tensor, and then we just focus on 3 tensor only. So what does it mean by the 3 tensor isomorphism problem? So here we have the idea is we have 3 tensors, and then we have an actions of the GLN on GLNQ on this 3 tensor by we action on the left, on the right, and also this side. So there are 3 sides of the tensor, and then we action on 3 sides, and then we get another 3 tensor, and this is D here. So the 3 tensor isomorphism problem is given 2 3D tensors, decide whether they are isomorphic in the sense that whether there exist A, B, and C in such a way that A, B, and C act on E, obtain D. And if you look at, if you look at the 2 dimension, for example, then you have what we call the matrix equivalent problem, right? So this is E, and this is D, and this is X on the left, and this is X on the right. And this is normally you see in multivariate crypto. So normally they have E is the center, the central map, and then you have linear map on the left and linear map on the side. So this is action, and you get D. So normally in multivariate crypto, they will have this one, and D will be the public key, and E will be the secret key, and those are secret key as well. But anyway, this is 2 dimension, and this is 3 dimension. Okay, and this is the 3 tensor problem, and so this is one problem that later you will see that they will be equivalent to ATFE. And this is one of the TI complete problems. The other problem is the cubic form isomorphism problem and quadratic form map isomorphism problem that you will normally see in multivariate crypto. The cubic form problem saying that given 2 cubic form is just homogeneous degree 3 polynomial. So polynomial that is homogeneous and of degree 3. So F and G, and ask whether there exists an invertible matrix A in such a way that A acts on G equal to F. where the action is just X on the variables. Yeah, it's the linear action on the variable. And quadratic form math isomorphism problem, saying that given two triple of quadratic forms, they are homogeneous of degree 2, and decide whether there's this two matrix that is mapping F into G or not. So the action is A action on GI in such a way that F equal to Fi prime is just the action, the linear actions of B into the Fi. Yeah. And the result that I mentioned earlier into series work of Yuming Chao, Pro Chou, and Tang last year, they showed that actually 4 problems, they are equivalent under polynomial time reduction. Actually, there's another problem. If you look at in the papers, there will be another problem come from group theory, and they believe to be very hard in group theory. So no efficient algorithm for it. So anyway, those give us some worst case hardness, support for the alternating trilinear form equivalence problem. But of course, in crypto, then we use average case. And what is the average case hardness support for ATFL? So before going that, then I introduced several notions in cryptographic group actions. So you have recorded group actions of group on the set previously, and we call this group action is one way. So it's proposed by Brashard and Duong. It's like how long? 30 years ago. So they call it the group action in one way if there exists an element X such a way that AX is a one-way function. So AX is just a map from G to X such that the image of G is just the resulting action of G on X. Yeah. So if we look at this example, let's see P is just a cyclic group of order P, and G is just an automorphism group of CP. And then we know that the automorphism group of cyclic group is just ZP star. So this is the multiplicative group of ZP. And then now the group, now they will act on the set X. X is just a set CP that you throw out the identities, okay? By this one, A here now belong to G and G here belong to X. So it's a bit confusing with G is element in G, yeah? But just because here CP also the group, so I didn't know, but by G2, and then you will see the consistency with the DLP problem. So the action of the group on the set is given by G to the power A. So now alpha is one way by this definition, means that A of AG here will be one way for some G. And this is if and only if the DLP is one way. So DLP, this is just DLP problem, yeah. So should be familiar to most of you. And then recently, another definition for group actions is scheduled random group actions. And scheduled random group action found it is proposed independently by Chi, Chao, Songyun, and also in another paper in cryptographic group action application of Alamati, Luca De Feo, and Montgomery, and also Pachachnabits. So they found several applications in constructing scheduled random function, digital signatures, and also in this work in the cryptographic group action, they also have application in proposing the dual mode encryptions. So they have more application in crypto. And what is and it's relevant for crypto purposes. So what's the scheduled random group action? So the group action there is scheduled random if it's indistinguishable between the two distribution. The first distribution is just two random elements in the set. The second is distribution is two elements in the set. The first one is random. The second is is the resulting of the action of G on X, where G is for some G in a group element. Okay, so if we look at the previous example we have, then now we consider G is just a ZP star and X is as above. And now Gx on X times X diagonally means that one element in G, they will send a triple into G to the power A and H to the power A. So this is diagonal action. So what's in the first distribution is random distribution. It's just the triple GH and G prime and H prime. Okay, they are randomly element in the group or in X. But you know that because X also a group, and H here will be of the form G to the power A, and G prime will be the form of G to the power B, and H prime it will be in the form of G to the power C. And what is the pseudo random? Sorry, this is typo. Pseudo random distribution. This will be the triple GH, G to the power B, H to the power B. So you look at here, the pseudo random action distribution will be two elements, X and Y will be the resulting of X under one action of element. So here is the resulting of GH under the action of B. But you know that H on belong to CP, so this will be equal to G to the power A for some A. Then if you write H to the power B again, it could be GAB. So the pseudo random, I mean, in order to distinguish between random distribution and pseudo random distribution in this situation, mean you distinguish between those tuples. And this is actually the decision Diffie-Hellman problem. Okay, and then we conjecture that the group action underlying the ATFE is also pseudo random. Okay, so this is the worst case and the average case hardness support for ATFE. And what is the algorithm that we know for ATFE? Of course, ATFE, we can represent them in terms of, I think I missed that. I'll omit that slide. So you can only represent it in terms of matrices. And you can, so for every trilinear norm of a trilinear alternating trilinear form, you can represent it by norm of n over 3 elements in the field. So we, in the algorithmic point of view, the first is, okay, we have two trilinear alternating trilinear form, and we would like to find element that map this form into the other form. Then the thing is we can do proof force, right? We can do proof force, and this run time is this one. We can try to adapt the dynamical programming method that is proposed in Lee and Chow, like 5 years ago, to the ATFE, and this will be runtime a q to the power 1/4 n squared. Actually, in those papers they propose for graph isomorphism problems, but this can be adapted to ATFE. Another work in the work of Grocho, Chow, and Tang, they propose an average case algorithm that attacking ATFE in time q to the power on, but it's work for on but some fraction of alternating trilinear form. In terms of quantum algorithm, then ATFE can be formulated as a hidden subgroup problem over GL and Q, and there are no known efficient quantum algorithm yet. And it is So if we, I mean, in lattices, you know that some lattice problem can be formulated at a hidden subgroup problem for dihedral group. And so, so excuse me. So my kid is just close the door. Thanks. Yeah, sorry. And then there's no known also efficient algorithm yet. So this is something we, of course, we don't know yet, but at the moment we can ensure that there's no not yet quantum algorithm for cutting hidden subgroup over GL and SQ. So we have some, of course, maybe in the future they may there's some algorithm. We can incorporate like Grover search algorithm to speed up, but not yet known some efficient quantum algorithm. So in term, if you look at, we can always representing or trilinear or alternating trilinear form, like we can look at it. At you see previously it have relation equivalent with the isomorphism problem coming from polynomials. So we can try to find look at the attacks against multivariate crypto to this ATFE. So the first, I mean, the most useful tool for doing this is Rockner-based attack. So we investigate Rockner-based attacks, and we also investigate the min rank attack. So one of the attack again mean multivariate crypto. So how can you have a rank there? Of course, for the alternating trilinear form, if you fix one argument, then you reduce to the k of bilinear form and you get the rank there. We do experiment on that and also Rockner-based attack. And what we get the asymptotically, we get the complexity for solving ATFE is this one. And this is somehow much better than previous one. But this will be the base case for us to choose the parameters. Here, omega is just the matrix multiplication exponent. So you see that ATFE, we at the moment we have several support for the hardness. So we believe at the moment that okay, it is somehow secure, and they have procedural random group actions. This is also conjecture. We have some theoretical support for it in the paper if you want to read in details. But it's still conjecture that this is pseudo random. So we have some belief saying that this is okay. This problem is somehow hard, and we try to build the cryptographic primitive on it. So here is the description of the basic protocols from ATFE. So now the public key will be two trilinear alternating form. And they are equivalent, similar to the graph isomorphism problem. Yeah. And then the secret key will be a matrix, invertible matrix. So I write A inverse for convenience. So in the first step, the prover just sample randomly on invertible matrices in GL and Q, and then it acts on phi 0 and send the commitment to verifier. Verifier just randomly choose random bit and then send to the prover. The prover set the response at B plus C times AB minus C, B. So if C equal to 0, then the response is B. If C equal to 1, then the response will be A times B. And it's sent to the verifier for checking. This is clearly that if the challenge is 0, then you know that psi just phi 0 compare with B and it's correct. And if C equal to 1, then you just compare with phi 1. Then phi 1 equal to phi 0 compare with A inverse. So A inverse with A, it's just identity, and time D and just time B, it's just phi 0 compare with B, and this is psi. Okay, so this is the basic schemes. And of course, for the security, it's easy. So it just follow graph isomorphism protocols. So given the challenge, you can easily assemble response first, and then you compute a commitment, then you have a accepting transcript, and this is indistinguishable with the real one. And for the sound, it's easy if you have a two accepting transcript, and you can easily compute A in such a way that A is solution for the promised alternating trilinear form equivalent problem. Yeah. We can extend the challenge space from binary to bigger size. So, well, the idea we inspire from the work of Defel and Gabrecht in the context of isogeny-based crypto. So here, instead of having two trilinear form, we extend to k trilinear form, and then we have k-1 secret, and they are all equivalent to yeah, I mean the public key, they are all equivalent. So the first round is similar to what we see in the basic scheme. The second is the challenge come from the space from 0 up to k-1, and then for the response, this is similar, but instead of time c here, then we denote it by psi of c. So if c equal to 0, we have b, and psi of c is just 1 if c is greater than 0. So if c is 1, for example, then this will be A1. We use A1 to answer it. If c equal to 10, then we use A10, the secret key, to answer it. And then for checking, it's just similar to the basic scheme. And of course, we need to repeat it to attain the required security level. And it's similar with isogeny-based crypto, then it's whether we can extend it into the exponential challenge space. Okay, so this is the parameters. We look at the choice of k, also the choice of k, and the choice of the number of the repetition. They have trade-off between the efficiency and so on. So we based on the analysis from the algorithm point of view, and also the trade-off between the k and the number of repetitions. Here we provide 4 options for the parameters of 128-bit securities, and this is the sign by, and this is the time in microsecond. So this is somehow the option 3 give us the better choice in case of public key, secret key, and of course signatures a little bit more, but in terms of some of public key and signature, then it's still better than other option. Of course, this cannot compare to what we see in NIST competitions like Dilithium. I think if I remember, Dilithium, they have around 4,000 in total, right? Secret key, no, the public key and signatures, 5,000 or 4,000. So the thing is here, our scheme, we don't have optimization yet. So this is quite basic description. So hopefully, if one can find some basic, some optimization method, then we can try to improve, reduce the signature size. Yeah, and this is something that we are working on. And of course, this is secure in ROM under the hardness of the M instant, like promise ATM FE problem. The question is, how about security in QROM? Recently, you see that there's several work regarding the security of Yashamir transform in QROM. And those belong to, I mean, our design is just Yashamir application for apply Yashamir mechanism, right? So the question is whether our scheme can be obtain the security in QROM or not. And we look at those, and what is the condition that we need is somehow we need to establish what we call quantum computational unique response properties. And this is somehow equivalent to ask the question in the context of ATFE. It should ask that whether, okay, I give you two trilinear, alternating trilinear form that are equivalent, whether you can produce two different matrices that acting on side given phi or not. So if you look at this property, then this is equivalent to a b minus 1 acting on psi fixing psi. Yeah, and this is mean that a b minus 1 belongs to the stabilizer of psi, and the stabilizer in this way we call the automorphism of psi. Yeah, fixing it, and this means that a b minus 1 is just a non-trivial automorphism. And then we come up with a problem saying that given an equivalent alternating trilinear form, and can you tell us whether the automorphism group is trivial or not? If not, then can you compute a non-trivial automorphism? Because if we can solve this problem, then we can answer to the question whether our scheme is secure in QROM or not. Yeah, this is something that we are also working on. So for the conclusion, what I try to say, ATFL is somehow potential for cryptographic constructions, but at the moment only signatures at the moment. They have a strong mathematical algorithm complexity support for the hardness, but as I say, they have limited construction only for signatures at the moment because the group there is non-commutative, as you see. So this is not that easy as, I mean, if you look at isogenes, it is commutative. So it is possible to construct more scheme in isogenes compared to this kind of group at the moment. So they still have a lot of work to be done in this area. And we hope to see those possibility or impossibility in the near future. So this is all for my talk, and thank you very much for your attention. I'm happy to answer some questions.
Thank you very much, Tom, for your very interesting talk. Maybe I'll start with the questions as the others think about them. Could you go to this table where you had the efficiency results? What is K roughly here? The size of the challenge space?
Ah, okay. I forgot to record it. Let me look at the. I think it's the number of C is 5. So 5 to the power 30. I think it's around 30 or less than 30. I think.
Ah, okay.
Yeah.
No, not too.
Yeah. Because we need to balance between both, so that's it. Somehow we.
Yeah, I guess when K, like the public key size is linear in K, right?
Yeah, you see.
That's why. Yeah, you don't want
you see. Yeah.
Yeah. And also, so in the protocol, so the challenge, I guess, can't be a vector or a scalar because you will lose. I mean, you don't have commutativity. That's why you don't use them. Is that right?
You mean the challenge?
Yeah, like using a vector or a matrix challenge.
No, because no, I mean the nature of the construction is not, because if you look at the vectors, this is not possible, right? Because if you multiply by vector, then it's not. Yeah, for this kind of scheme, we cannot use vector here, I think. Is that what you asked, or?
Yeah, I mean, like in general, a matrix, not necessarily a vector, but a matrix of a proper dimension. But I guess, yeah, since it's not commutative, I think that does not work for correctness.
Yeah.
Okay. Yeah, but very interesting. Any other questions from anyone?
Yeah, hi Dung. Yeah, thanks for the nice talk. Yeah, I was wondering about the the attacks. So in the you had these several attacks that you considered, right? Yes. So for the last class of attacks, the multivariate, did you use any quantum algorithms here, or it's just the classical attacks?
I think this is classical attack that we run experiment. Yeah, in quantum shot you can yeah, for quantum then you can improve a little bit. Yeah.
Yeah, I was wondering what effect does it have on the complexity, or do you know?
Yeah, I think this is what we try to do the, so this is what we do for the classical one. We haven't, I think, incorporate the quantum yet.
Okay, yeah.
Yeah. But for quantum set, maybe you can reduce.
So is that like using Grover in there, or?
I mean, yeah, in case you can, if you can do quantum, then only Grover is relevant, right?
Yeah, yeah. So do you know also for the
I don't know any quantum algorithm for Rockner basis yet.
And for the fourth problem, like the hidden subgroup over this GL of NQ, so are there any known algorithms?
I suspect no, because there are no not yet for the GL and Q. I think they so for, I think they for non-commutative group, for hidden group subgroup problem, then it seems to be hard at the moment. So for the, like for symmetric group, then we also don't know yet any efficient one, right?
Yeah.
No, we don't know any. So that is something that we're not aware yet with the quantum algorithm against ATFE at the moment.
Yes.
Yeah.
Okay. Yeah. So for the parameters selection, you use the last complexity, this Q to the 2/3 n is the one that you use for this.
Yeah. Yes.
Okay.
Yeah.
All right. Yeah. Thank you.
Yeah. Thanks for the question. Yeah.
Sure.
Yeah, maybe related to what Ron mentioned. I guess there is no proof for this, but do you have an intuition? So you mentioned that the relation of ATFE to lattice problems and also multivariate crypto problems. Do you have an intuition where kind of ATFE sits? Maybe like, do you think that it's harder than these things, or maybe if it's
is it proof? Is it proof by the work of Yumin? They prove that they are polynomial time equivalent.
But wasn't it for the hidden?
So they have here, they have they are equivalent under polynomial time reduction.
But I mean, if you compare ATFE to, let's say, like cis.
No, HFE is broken with the choice of parameters there, right? So HFE, you mean hidden field equations? Yeah.
For that, there is a proof, I guess. Is that true?
I think no, there's no proof for that one equivalent to this one. Maybe no.
Wait, sorry. Yeah. Okay. Yeah, this one is actually not there. Do you have any intuition where would this one sit in terms of the hardness compared to?
I think in terms of the complexity, then I would suspect ATFE is more complex.
Okay.
Yeah. But this is maybe so the right people maybe to answer this is, I think, Yumin. So he worked more in the complexity and computational point of view.
Yeah. It's good to see new flavors of problems.
Well, maybe I can ask also another question, but how is it how is this ATFE problem related to the, the problems that they use for the other multivariate schemes like Rainbow, for example, or the other signature schemes that proposed based on multivariate?
So if we look at so Rainbow, it is quite similar to quadratic form map. Well, isomorphism in the sense that if you look at Rainbow, it is similar to this problem with the change that they don't use quadratic form, but they use normal polynomial of degree 2. And the relation is, but for Rainbow, I mean the central map of Rainbow is quite different from the central from this problem. This problem is just random element, but those in the Rainbow, I would say that the central map is special. Of course, like Rainbow, you can formalize in terms of quadratic form map isomorphism in the, and then F and G here are just not homogeneous of degree 2, but it's just polynomial of degree 2. But the thing is that the center map in Rainbow, they are spectrals. Spectral, they have a form of they have spectral form. There's not random. So I suspect for general Rainbow should be of course I don't have any proof, but I suspect the form there should have more structures than those general problems.
Yeah, this one is more random because you choose the matrix at random, right?
Yeah, and also the vector, the F and G here, they also random. So I X random. Right. But there the structure of G in of F, for example, of G, for example, in Rainbow, they are different. So they have 2 layers. The first layer they have less number of variables, and the second layer they have a whole. So the whole number of variables. So for example, you consider on the ring like x1 up to xn, then the first layer of Rainbow, they just consider like partial portion of variables, where so the polynomial doesn't cover all the variables in the ring. And the second layer they have all the polynomials, all the variables. Sorry.
Okay. Yeah, I understand. All right. Yeah. Thanks.
Okay. Any last questions from anyone else? Yeah.
That's why in Rainbow we consider also a lot of, I mean for the min rank attack, then of course in Rainbow this is somehow relevant in the sense that they need to be careful with that, and based on that choosing parameters. In our case, we try to investigate min rank attack again multivariate crypto, or again this one ATFE, but we try all the way, and this is still not I mean not as good at Rogner-based attack that we try to do. So min rank attacks is not that we should not be aware of at the moment. So
okay, yeah,
does not give much benefit in terms of attacking. Yeah.
So the best known attack is the Grosvenor one, right? Or...
Yeah, we base on Rogner-based attacks.
Yeah.
Yeah, for the direct attack, then yeah, this is only the attack that we be aware of. So any like any any way of using Rogner-based attack, we should be aware of that one. So yeah.
Thank you.
All right. Yeah, I think if there are no more questions, we may conclude the session here. Thank you, Dung, for your very interesting talk. And thank you, everyone, for tuning in. hope to see you in the next seminar.
Okay, thank you everyone, and
Thank you then.
have a nice weekend. Hope to see you in
Bye-bye.
Golomon. Yeah, bye.
See you. Bye bye.